Our next speaker is Eugenio Culurciello. So Eugenio is professor at Purdue University. He's a very well-known researcher in the domain of hardware machine learning. He's one of the co-inventor of NewFlow, which was one of the very first deep neural network accelerators. And recently he's been the co-founder or founder of ForwardNext.
Thank you for the introduction. Thank you guys for staying this late today. It's a pleasure to be here. So since it's an architecture conference, I figured I would tell you a little bit about our latest architecture, just to switch gear a little bit. So all this work here was done, a lot of the architecture was created by Vinay, the first author, and implemented by the second two guys. The why, I think, you know, most of other talks have explained why we try to do deep neural network hardware and why it's important. These are just some results from our lab in the recent years. So obviously these algorithms are here to stay, and they'll help us to navigate our cars and translate our language and so forth, right? These are other possible applications. I think the one that I like the most these days is augmented reality and personal assistance, because it will give you sort of superhuman power by connecting your visual experience to the internet. I'll get into this maybe a little bit more later if we have some time. So, but today, if you want to do deep learning and basically you know, if you want to train and execute this deep learning algorithm, you pretty much have one choice. So, yeah, so NVIDIA has been doing great. Thank you, Bill, for all the great work. But you know, what if I told you that we can put all this compute in your pocket, basically? This has been our goal for a while. I guess most of you are familiar with the workload. So workload of especially convolutional neural network for vision, which are the kind that we mainly target at this point, is we have to implement convolutions, and they are basically very embarrassingly parallel portion of the algorithm, and they take most of the workload. So. But again, this is not the only application. Other people have mentioned, you know, translation and MLP and reasoning require other kind of operations. But at least for convolutional neural network, convolution are the main workhorse. Then you have max pooling operation or pooling operation, where they take just a small percentage of the workload. And then you have a fully connected layer, which usually require a lot of memory bandwidth, as you've seen, and mostly Mac operations. So we try to basically come up with an architecture. We developed in the last 10 years, we started this work with Jan LeCun and back in 2006. And over the last few years, we basically implemented multiple architectures. I think the previous one were mostly six-tolic array, but we couldn't really figure out how to properly utilize six-tolic array to 100%. So we decided, and this was basically our limitation of previous design. We couldn't get 100% hardware utilization on executing this network. So we decided to start from scratch, basically, and this was our design goal, try to get to full utilization of the hardware, because if we get to that point, I thought, okay, maybe then there's not much else to do besides reducing power. So our accelerator is composed, like many that you've seen today, by an array of multiply accumulate unit, some on-chip memory, local caches, and a small CPU to orchestrate everything. So I want to show you some of the kind of parallelism that we can exploit in this computer architecture while executing a convolutional neural network. And most of you probably are familiar with this. But so one of them is intramap interactivation. So the MAC share both the both the input operands. There's intramap interactivation. So you share the weights, but you don't really share the inputs, the same inputs. There's the intermap, where you're doing two output maps of convolutional neural network, different parts of it. There's really no data sharing. You're not sharing the inputs. You're not sharing the weights. And then there's interlayer, where also there's no data sharing. It's like you're executing two convolutional network or two neural network in different part of the hardware. So these are important. We'll go back to it just to show you how we implement all of this in our architecture. So I think the key point of our new architecture and sort of the key idea of this, which is now patented and our company Fornex is licensing it, it's basically this idea of trace. So what we try to do is we try to figure out what is the longest computation that we can do. How can we organize the data so that we have the longest number of computation in a sequence that are contiguous? Once we figure that out, basically, and we have these very long traces, it's very easy to then hide the preparation of the next computation behind this latency. So this was really the main idea. If you look at basically what a GPU that does today, or it basically takes every core decodes instruction, at least before they had the tensor unit, and every instruction basically multiplies two numbers, right? Instead, in our system, what we do is we basically have a single instruction. It's like a SIMD instruction that operates on this long trace. We do all this operation, we issue this instruction, and then we're ready to create the next instruction. In order to find sort of the best organization, this might be obvious to many of you that work in architecture, we found that the best organization of data is if we organize the data in the depth minor. So if we store kernels and memories in the Z dimension, basically. This allows us to have a number of contiguous operations that are, from 3 to 2,000, and usually on the order of 100 or several hundred operations that are contiguous, as opposed to if you organize it in a more simplistic fashion, like by row or column major, where you don't have this much parallelism, right? So, and creating this trace basically allows us to utilize all the hardware and prepare the next instruction. So the way we do this is, so we have, we figure out, we take one of these trays as long as possible, whatever fits in our caches. So let's say we can take this entire, this is like a kernel and this is like a map. We take this slice of both the kernel and the map, and then we break them down into small amount of vectors, because usually vectors for us are 16 numbers. So more manageable unit that is also similar number are used by AMD and NVIDIA as well. And then, yeah, so what we do is we basically, in order to create one output pixel from the multiplication of these two cubes, we basically take a sequence of a trace and a sequence of the maps and kernels, and we multiply them together, and we keep accumulating them on a single output. So that's fairly standard, no news there. So the way that we do this is we have some MAC array, and we split up these two arrays, the maps trace and the kernel trace, into 16-bit slots. Basically, this is the value of every pixel, and we multiply them together in this fashion. And so, maybe hard to see, but we take the first sort of little slice like that, and then the second little slice, and we keep doing this for a while until we completed the whole operation. So this is called in our architecture the cooperative mode. The kernels are basically shared by all the Mac multiply accumulate unit. And at the end of this operation, we need to, at the end of all this computation, we need to do a partial sum, basically add all these values together to produce the output. There is another case, so this is all good if the input and the output are a multiple of 16, for example. It fits very well and we have pretty much 100% utilization, but there are other cases where you don't have 16 inputs or 16 outputs. For example, in the first layer in a convolutional neural network, you only have 3 maps, right? Or if you have a number that is not divisible by 16. So in that case, we use another mode. So basically, we take different pixels, different kernels pixels, multiply by the same pixel in the map, neural maps. Okay, and so we take the first slice, and then we take the second slice of this, and this is called the independent mode. So independent because basically every Mac unit is producing one output. Before, in cooperative mode, they were all working together to produce one output. Now they're producing 16 outputs or n outputs, right? At the end of this, we have to have an operation where we add biases, but there's no reduction operation. We get 16 output out of this. And also, again, in this mode, we can keep very high utilization as well. So just a couple of details about our architecture. So the main unit is a vector multiply accumulate. So it's just an array of multipliers, 16 of them. There's a unit that there's a shift register that does this accumulation and add the biases. Each one of these vector units has a 1 kilobyte memory, cache memory. And then the maps is basically shared across 4 of these VMACs, so 64 Mac unit. And this is 64 kilobyte cache memory. So we have basically the equivalent of 120 kilobytes per compute unit. We call this compute unit because it's a cluster of 64 Mac units. In order to do max pooling, we basically had another operator in parallel to these VMAC units, and this is basically just looping over the pixel to find the max, right? So the idea though is that we can run max pooling on a part of the image that has been already convolved while the rest of the convolution, while these VMAC are processing the rest of the image. So we can basically hide all this latency behind the Mac. We don't really lose cycle by doing it. So this is how you would scale with compute clusters. So each compute unit here, there's 4 of them, 4 compute unit per compute cluster, and then you can group them together with a memory interface. So another small details is that each one of these compute clusters have a small CPU. So for us, is our own little RISC pipeline, which decodes this SIMD instruction, fetches and decodes them. But we have one for every 4 of these compute units, basically. So yeah, just to go back to the parallelism that we can exploit. So for intramap interactivation, one VMAC in co-op mode can do this kind of parallelism. Intramap interactivation, so there's 2 VMACs across a compute unit can do this. This is 2 VMACs, intermap 2 VMACs within a compute unit can do it. And the intra-layer could be, for example, Vmax across two clusters, different clusters of compute. So this is not just an architecture that on paper, but we actually implemented the whole thing on FPGA to prototype it. FPGA are just Lego blocks for circuits, and so we can test. But this whole architecture basically built for scalability and for SoC implementation. So we implement 256 MHz system that runs at, in this FPGA, 250 megahertz, which is basically as high as we can get. This is an older FPGA, so it has a pretty bad memory bandwidth, only 4 gigabytes per second. So this board would consume like something like 12 watts. Okay, but it's just a prototyping platform. And then what we did is we benchmark on free neural network that are fairly popular. And with benchmark, I mean we really run the entire network end to end. And this is was at least one of the few publications that was comparing was able to run all these architectures. So in AlexNet, you can see this is what we were aiming for. We were aiming for 100% efficiency. So we pretty much have it everywhere, but in the first layer. So in the first layer, a lot of the inefficiency that we have is because of this reduction operation that we have to do. With the shift register in FPGA, we couldn't implement a tree array like we would be able to do in SoC. So in SoC, this number would be close to 100%, but here, unfortunately, it's a bit lower. But if you look at overall, still on the entire network, the efficiency is pretty high. These are the results for GoogleNet. Again, you can see exactly the same problem here. Wherever we have a small inefficiency here and some of the inception layer is because this inception layer have some numbers that are not divisible by 16, and we have to use this independent mode. And in this independent mode, we don't have a good reduction operation. Yes, sir. Frames per second. I think I have it in a later slide. Let's see. Yeah, we also ran ResNet 50. As you can see here, the first layer is exactly the same problem as the other network. But in all the other layers, although it's a fairly complicated combination of convolution blocks, we still run pretty close to 100%. So yeah, these are results, for example, for performance in terms of bandwidth. So the bandwidth utilization, I mean, it is what it is. These are like a standard network, right? But our design was also, this design was also created to reduce the number of the memory bandwidth with this multi-cache system. And so the maximum that we have is about 3 gigabytes per second on GoogleNet and ResNet 18. So we're still within the limit of the FPGA. Again, if we were running higher clock, then we would need faster bandwidths. So it did work. If we run, we actually have a demonstration system. If anybody is interested to see it, contact me. But you know, it basically runs this network and produces the right results. So this is a bit of a comparison of our accelerator called Snowflake with some recent work in the accelerator arena. Again, you can see that the idea for us was to optimize for efficiency, and I think we have one of the best efficiency. The one that comes closer to us is running at a much lower clock. And when you run at much lower clock, it's easier to hide latency, problems with latency. So there is one thing to say. Most of other designs implement some kind of a systolic array. Like I said, our previous design was also systolic array, but we were never able to maybe have a smart enough compiler to fully utilize it. I think Google has done a really good job at it, from what I can tell. I like to know the tricks. These are just some projection that I wanted to give you. So if we were to design this accelerator on an SoC, right, which is where we want to go, in collaboration with our company and some silicon partner. Basically, the idea is if you compare to Google TPU, and we have, if we could scale the system to this many Mac unit, we would have slightly better performance because the system is designed for 100% utilization. What's more important for us is, this is performance per watt. So basically, this is a very, very small, very optimized SoC that only does this kind of operation. While maybe it's unfair to compare it to a GPU because you can do lots of other things. And also our system is now at 16-bit fixed point, which we found it to be enough for most of neural networks so far. But obviously we could go lower bits, and we can use all the other tricks like compression or sparsity and so forth. Right? Nothing would really change. So yeah, this is pure performance, and what I wanted to show you has a little version of our chip, so 1,000 Mac units. So scaling our system basically 4 times would give you pretty much the same compute of a Titan X board, and that's more or less where we wanted to go. Put it in your pocket. So beside hardware in the lab at Purdue, we also do work on algorithms, and one of the things that we're very interested in is, for example, augmented reality. In augmented reality, I would like to have always-on assistant that is looking at what I see and basically predicting my needs, right, and helping me. So we need something that it's like our brain in a way. We need to kind of predict the future, right? So we designed this new kind of neural network. This neural network is both feed-forward and feedback, but it also has recurrency. To solve basically a lot of the limitation of standard convolutional neural network, for example, output stability and so forth. So this network right now, in this example, is trying to reproduce the next frame in a video. So this is like the current frame, this is the real next frame, and this is the next frame that our network predicts. And so it does a good job to reproduce the pixels. And it was also designed to be stable, create a more stable output. I don't know if some of you have tried a standard convolutional neural network trained on images, you'll see that they do really well for a while, and then all of a sudden the performance drops because they're not trained on video. They just don't have any concept of time and everything. And here you see an example where we basically use this neural network. This is a standard neural network, just the feed-forward part, and this is the entire, we call it cortex net, the entire cortex net. You can see that its output prediction of chair is much more stable than what it used to be. There's a lot of more work to do in this kind of neural network. We're still studying them. They bring in some complication in training and so forth, but we think they are. One thing that I should mention is that they can be largely trained unsupervised, so sort of predict the next frame or the next representation. They don't really require a lot of label data, which I think is a prerogative to do things in real life, real world, because if you want to prepare for the real world, there are just too many examples. You're never going to be able to label. So we need something that learns sort of the bulk of the knowledge of your environment, and then can, with one-shot learning, we can transfer the knowledge of one task or one label to the network. We also need some network that don't forget what they learned. So this network also was designed by able to predict the future. It basically knows So if we can predict the future is correct, and it doesn't need to learn something new. But if we cannot predict the future, it actually has a built-in signal that tells him, hey, you need to pay attention to this example, you need to learn it. This is something that standard neural networks don't have. And so this would allow them to do to learn new knowledge and do online learning. But again, all of these things are under study. Keep an eye on it. So for us, in terms of future, what we're going to do with our architecture is we're working on scalability right now to 1,000 and 2,000 Mac units, doing SoC optimization, so getting ready for producing an SoC. What we really want to do in the very, maybe more 2-3 years terms is one, we want to create a neural network that will compile code for this architecture. Because compiler, I haven't talked about it in this presentation, but it's actually one of the hardest things when you build this kind of stuff, especially if you're not, like me, in the right field. Right? The other thing is we want to have neural network design hardware for us. I think it's been mentioned. I hope this is the last architecture that one of us will build, and I hope that neural network will find better solution in hardware like they found it in many other fields. And with that, thank you guys. Any questions?
Thank you very much. So there is a question down there, Luis.
Hi, you mentioned that you studied systolic arrays and ended up moving away from them. I'm just interested to hear your comments about if you could elaborate on that.
Oh, sure.
Why you don't believe that that's the way forward. I'm a believer, by the way.
Yeah. So we worked a lot on streaming architecture, streaming the data in without caches. And it was always hard to fit different kind of convolutional kernels. So if you have a set of Mac array, like we used to have 10 by 10 or 12 by 12, right? If you have a 12 by 12 array and you need to do a 7 by 7 convolution, there's a mismatch there. Like either you need a smart compiler or you're not going to use a lot of these things, right? And then if you have a 12 by 12 and you can break it into a grid and do multiple 3 by 3, I'm really curious, like I said, to see what Google does in the TPU, because they seem, at least in the paper, it seems like they are able to get pretty high efficiency with a very large array. It's like 250 by 250. I cannot just imagine that, but maybe it's just my ignorance. But basically, yeah, it's purely how you map these algorithms, this multiply accumulate to this big array. In a systolic array where you're streaming data in constantly, and it's just, it was hard. So that's why we designed, this architecture is much more granular, if you allow me. So, we have more control. Again, compiler is tricky for this too, but at least, like I showed you, we can get there. Yeah.
Yes. I have a quick question. So could you elaborate a little bit more on where does the better performance for what come from in your architecture? Is it because of the trace trick, or what's the gist of it that makes it better than?
Yeah, no,
CPU
I would say if NVIDIA has a tensor processing unit, a tensor unit, and Google has designed a tensor unit. I think if we put them all in the same process, you wouldn't see much difference. Really, the question is, can you go to 100% efficiency? I think once all these architecture go to 100% efficiency in the same process, I don't see much difference between them, because it's just a matrix 2 vector multiplier. But maybe it's just that I'm short-sighted right now. Yeah.
So I have one more question, which is, you seem very focused on the efficiency, the utilization.
Yes.
I understand the utilization as the number of cycles where the max are used, basically the fraction of max used every cycle.
Yes.
Is that correct?
Yes.
And so logic is comparatively quite cheap with respect to memory, for instance. So does it really make sense to completely be focused on the utilization of the max?
Well, no, I mean, there's other things that come into place, like memory bandwidth. So this architecture, from our studies at least, has a much lower memory bandwidth than on a systolic array. At least our previous experience had a lot lower, and it also, again, because we have local caches there, and we can cache kernels or maps. We have a lot of data reuse. So memory bandwidth is pretty low, and it was also one of the main point of this architecture. The other is power, I would guess. So, how can you make this computational unit consume the least amount of power? That is the third dimension that needs to be explored more, maybe. But yeah, I think we were going for both, basically, just to lower as high efficiency as possible and as lower memory bandwidth as possible.
I think there is another question.
Yeah.
Yes, sir.
You mentioned that you're building a SoC at the 40 nanometer node, and before you also mentioned that your goal is to get into the small device.
Yes.
So aren't you selling this as an IP to somebody like Qualcomm, or why are you building an SoC?
Yeah, so right now we are basically working on strategic partnership with SoC manufacturer, because it's, they're already set up to do it, and why would we have to reinvent? That's our goal. If not, we'll do it ourselves. That's basically the plan.
And maybe I have a last question. So you mentioned at the end that you felt the compiler was the hardest part, and yet you started by optimizing the hardware rather than really working on the compiler. Is there a rationale basically for that, or?
Okay, so I have to say, so the hardware was optimized. We looked at all this neural network architecture, and for every block we designed it. I guess there was some compiler thoughts there, right? So we designed it to so that every layer out there would be able to reach to 100%, right? But then designing and we can handwrite code that shows that in in any case we can get there. But the question is to make a very general compiler that for any kind of input, any kind of kernels does this. That is the tricky part, right? That requires some. We're a small team, so for us it's for Google maybe it's no big deal, but for us is where we need to put more cycles.
Okay.
Yeah.
Okay, let's thank the speaker again.
Thank you.